the group which includes both translations and Lorentz transformation is called inhomogeneous group, inhomogeneous Lorentz group. It's actually simple answer. So in this case, we have the following transformation. X prime mu, which is equal plus A mu. Okay, without this term, this transformation homogeneous in A. When I put constant, it's inhomogeneous. That's it. So this is why it's called inhomogeneous Lorentz group, because this constant breaks homogeneity of the equation. Okay, so let's go further. We derived this Euler Lagrange equation, and now let me consider. Let me start. Okay. We also have in this case, besides Lagrange field theory, Lagrange formalism, Hamiltonian field theory. Like in classical mechanics we had. Okay. Now, introduce momentum density. Not momentum, but momentum density. And this is this. Phi x equal simple derivative d with respect to time derivative of field phi. It's like in the case of mechanics, we had q and dot. We have now phi dot. But it's called, so this is definition, one to put identical. Okay, then Hamiltonian density. You see, we had Lagrangian density. This is not Lagrangian, right? Lagrangian is there, actually, right? This is, by the way, right. So Lagrangian is exactly, one can write d3x, spatial component, and you have this phi, right? Then we have Hamiltonian density. It is and this guy is this phi x phi dot x minus Lagrangian density. So same structure, but it's density. Okay, now Hamiltonian, which gives energy to us. This is just H, and this guy equal d3x, and we consider Hamiltonian density. Okay, now example. As example, we consider very simple theory. Consider Klein, Gordon, KG theory for a real field phi x. Okay. And this guy, we should write Lagrangian density. Field theory starts from Lagrangian density, usually. And this is this guy. We can rewrite it in more explicit way. So I divide this in time derivative and spatial derivative. So first is time derivative, then minus 1/2 grad phi square and 1/2 m square phi square. Okay, so we will see that in quantum field theory, this theory describes massive scalar particle with mass m. We will see this. This is still classical. And we will show soon that this theory is Lorentz invariant and phi x assigned to representation 0, 0. So this is scalar representation. It's invariant under Lorentz transformation. We will show this later. But now let's consider this as given from heaven and let's analyze it. Okay, equation. Let's consider Euler-Lagrange equation in this case. They're written on my right. L is known, so it's quite easy to calculate them. Okay, so first term, you should take derivative of this term, m square phi square, right? So we will get minus m square phi. And now second term, x like shown on my right, and result is this d mu phi equals 0. So this is linear PDE, and it can be rewritten in this more explicit form corresponding to this, like that, minus m square phi minus second derivative with respect to time and plus grad square phi. This is, of course, Laplacian, right? And this is equal 0. Besides this mass term, this is wave equation known in PDE. So it's quite a simple equation, right? Please.
Coming from the second term, that Euler-Lagrange equation, the partial of mu.
This.
Yeah.
Right.
And the second term you get there in the resulting equation comes obviously from the first term above.
Yeah, from this one here.
You have the product of two partials. And now you take the partial with respect to...
Yeah, I take derivative with respect to this stuff. For example, it's written here with respect to d mu phi. So I should take, say, this, right? For example, then I get this stuff and still another derivative. So I have two.
Oh,
Look.
I didn't see the half. Okay.
Right. So you took derivative with respect to, you got one derivative, but still you should by hand put another one.
That's what I was wondering about.
And then you have two because you have you should consider derivative of like square. Okay. So we have this answer. So this is Klein-Gordon equation. Okay. Let us find Hamiltonian. Okay, so let us find Hamiltonian. We should find first, of course, Hamiltonian density by using that expression, right? And then, okay. And then find Hamiltonian. Okay, so I will start here, use this Hx, just that formula, equal pi, oh, sorry, right. We should find pi x first, right? I have not yet found. So let's find here pi x, which is shown there. This is d l d phi dot, right? And in this case, this is this guy equal just phi dot, because we have this term, right? Now, let me use this blackboard to get, for this theory, this density. This is pi x, phi dot x minus L. Everything is known here. So what we have, I could write this first term as pi square, because phi dot equal pi, right? And then minus L, which is shown here, right? So we have 1/2 pi square x plus 1/2 square and plus 1/2 m square pi square, and this is equal pi square 1/2. I will not write now argument, plus 1/2 this is Hamiltonian density, and H is this d3x, and we should substitute what we found. Okay, so I could put something like H, this will be 1/2, and I have those terms, pi square plus grad phi square plus m square pi square. You can see that the guy is expressed only through momenta and field phi, no velocity, phi dot, like Hamiltonian should be. This is Hamiltonian. What is meaning of this stuff? This is, as usual, is like in classical theory, kinetic term, 1/2 pi square, kinetic term. This term describes deformation of my field, right? This is grad. So my field, when it depends on x, we have positive contribution, we spend energy. Deformation energy. Deformation of field, right? Deformation, kinetic term, deformation energy. This term, existence of field, you see, even So without if field equals 0, just 0, we have energy equals 0 here. But this term, even phi is only constant, like 1, 2, 3, we still have energy, right? Even without grad and dependence on kinetic. So it's a kind of describe existence of field, right? Okay. This is now another example, complex. Another example, complex KG field, Klein-Gordon. Okay, so in this case, L density, Lagrangian density is this. So it's still scalar, but we have complex guy. So it's complex field. It has both real and imaginary part. You can rewrite this like no 1/2 in this case. And there are two Euler Lagrange equation, right? So let's use EL for Euler Lagrange. Are two Euler Lagrange equations. And just check by yourself. They have this form. In this case, you have two, because you could consider variation. You could consider this, what we used before, considering derivative with respect to first phi star, then you will get this. But if you consider derivatives for phi, or you will get this. So just two independent Euler Lagrange equations. So as I said, first consider this equation variation or derivative with respect to phi, and second with respect to phi star. And you will get to those equations. Okay. The momentum, we have the momentum densities. We have two. Phi, this is derivative of Lagrangian our density with respect to phi dot. And this is here guy, take, this is nothing else as phi dot complex conjugate. And phi complex conjugate is d l d phi dot complex conjugate, and this is phi, and this is phi dot, no star, sorry, just phi dot. Okay, now you have a Hamiltonian density. So we have this. minus L. Okay, and we will get this pi star plus where? Here?
Yeah, p phi dot is because
No, it's like that, right? So field and this pi phi. Mhm. Okay, so this is definition, right? But I substitute, right? Look, this guy equal pi phi star. So I substitute, all right? So pi phi star plus second term will be opposite, different order, but actually it's same term, pi phi star pi phi plus grad term and the last one and we can rewrite, sorry? Subtract. Oh, yes, thank you. Sure, you are absolutely right. Of course, I should subtract, yes, this term, right? This term, right? I should subtract this term, right? And I forgot. And this term is nothing else, this is important, minus, I subtract pi star pi phi. So this is cancel. And we have, let me write here. So we have this pi star. Then we have grad term. And plus m square phi star. That's it. So it's another model. Then, of course, you can consider Hamiltonian just integrating this term. No 1/2 in this case. Okay, so let me also write a formula. Maybe I can, so I use all of them here. All right, but I can. Let me write generalization. For general case, we have now Mn general representation of Lorentz group. How we can so general theory for phi ax, which assign in, say, some representation, right? Okay, it's straightforward. Action in this case S is we have Lagrangian density somehow depending on those fields. It's not, of course, Klein-Gordon. Klein-Gordon only for scalar field. Some general function, right? So, and d for x, the Euler Lagrangian equation looks like that. D, this guy, very similar. D phi AX. Sorry? Yeah.
About the previous.
Right.
Sorry. It's about the, is there any easy close?
Yeah, sure. Pion field looks like that. Famous pion field. A lot of particles described by this field. It's very physical field. Very. Many particles, not one.
Yeah, maybe one question about skeletal. Do we have the complete correspondence between complex skeletal and two real skeletal?
Right. You can rewrite, of course, you're right. But usually it's not convenient, actually. It's more convenient to use complex. But you are right. You can write real part, imaginary. Mathematically, it's equivalent, right? Point is that charged particles, charged pions, pi plus, pi minus, described by complex field. And this is what we measure, not combination of fields with different charges. Go ahead.
Fields that have their independent correspond to elementary?
Yes, they correspond to elementary particle, not composite particles. Pion, right. But in low energy region, pion is described by Klein-Gordon as elementary. Sometimes it looks like elementary when composite scale is much less than scale physics you study. Okay. This equation look like that. Same form. I will write. And A, in this case, 1, 2, up to m plus 1, n plus 1, right? So we have those system of PDE. Even in this case, we have two field, we have system, one field for phi complex. Of course, they are trivially connected through complex conjugation, but in principle, they are connected. Okay, now momentum density. Pi AX is this derivative. Oh. It's not good written. Usual formula, and Hamiltonian density is this. I will write more explicitly, just summation from 1 up to m plus 1, n plus 1, and pi ax phi dot x minus Lagrangian density. So a kind of straightforward generalization in this case. Okay, next we will consider Lorentz transformation of fields and Lorentz invariant field theories. Just general discussion. Okay, I believe I should. I do not have here, right? Oh, there is. I could start it with. Okay. Yeah, I believe. Right. series. Okay, it's discussed in 3.1 Peskin, but in a little bit different form, but quite close, many things. Okay, start from Mn representation. We know what is going on. In this case, m plus 1 times n plus 1 component vector field transform under Lorentz in this stuff, and we can write this is lambda and this is phi b. But now, what we want to consider this as field. But you see, under Lorentz transformation, we have transformation of both of the form like that, but also we have this transformation, x prime, x mu goes to x prime mu, which is lambda mu nu x nu, which I will call just lambda x sometimes. Okay, how we describe this, taking into account of both? So what is the transformation law? In this case. Okay, let us show that phi ax transform phi prime ax, and this guy equal m a b. I will not write m half of m half of n. Okay, right? To some general, and phi b like that. But now new thing. You should in argument put inverse lambda acting on x. Okay. Let us show why we should believe in that. Okay, let me. This is very important point, of course, for field theory, classical and quantum both. Okay. Let us start from scalar field. Phi x, which is assigned to 0, 0 transformation. So in this case, m is 1, no transformation of the form. So let us start from that. So let me even, when m lambda equal just unit, this is, it acts without any change identity. Okay, what we have, so let's consider some point. This is point x, I pick up in my space. And due to Lorentz transformation, this point became x prime, right? And x prime equal lambda x, right? Now, what is going on? During this transformation, what happens with this field? Form of this field does not change by definition. right? Because it's scalar field. So it's just taking from point X its value, and it put here. So what does it mean? New field after transformation, phi prime at point X prime it just equal phi X. So I took field at point X and put here because X prime is image of X. So very simple transformation. So this can be rewritten as phi prime lambda X equal phi X. Now take change of variable and call lambda X equal Y. Then we have phi prime Y equal phi lambda minus 1 Y. But Y is notation, right? So it's same like I could use instead YX, right? That's it. So you can see this is very simple meaning of that stuff, right? So this is transformation law. This is important transformation law in the case when M equal lambda 1, right? So new field point Y. So just this, at my point comes field which was value of the field which was before at point X, right? Sorry? Where I said? Oh, here, right. This is lambda X equal Y, right? Where? Oh, where I wrote this? Just here? Oh, here. By definition, I want to study field which does not change the form. We know this representation, 0, 0. I just pick up as example. Let's take the simplest case, okay? So M equal 1, identical matrix, okay? It's just example. Now let's consider the case of more complicated when we have non-unit matrix, more complicated representation, Mn. So what happens in this case? So here we have this. Now we have here some field, and because it's vector, let me just illustrate some in this point X, this guy has some direction. Now lambda transformation as before, this point X comes to point X prime, which is lambda X as before, but it could be different vector because form changes, right, of this guy. So it looks, say, in this direction. And now we have here field with different direction. So what we have in this case is that field phi prime, point X prime, like before, equal M, A, B. Here it was 1. Phi, B, and, okay, just one moment. Right, okay, right, M, right. Okay, and this is X. So I took this field, but during transformation, it changed the form by this operation MAB. But it came to new point, X prime, right? So this is this field. Now the same story. From here we get result that phi prime lambda x a equal m a b f b x, and from here we get this result. Changing, as I said before, we have this law. If you can say this, let's go lambda x replaced just by x, right? Then x will be replaced lambda to the minus x, right? So you can say this. Anyway, we got this. So you can see that field transform in more, it's actually simple formula. We have change of both coordinate and the form. Some questions here. Absolutely unclear, right? Unclear?
No, clear.
Clear? Really? Okay. Okay. Okay, very good. No, I'm just, okay, but this is the point. Anyway, now let's go further. Sure, sure.
We have phi AB, and then we say that the phi A. So phi
Oh,
A is
here
like
I
a vector,
put
yeah?
here A, right? Oh, okay. I was in hurry. You should. So here we have put, of course, phi capital AX, right?
And phi A is like a vector.
Yeah, for example, four-dimensional vector, and in different points, right?
And in the one that was like real and complex, instead of saying real and complex, we can consider two different fields. Isn't it different?
You can. It was already. It's a good question. It was asked.
Yeah.
You can do this.
Is it the
No question. Sure, you can do. But sometimes it's not good to do. Because, for example, complex field, scalar, describes some charged particle. It complex conjugation described field, also charged, but with charge minus the charge. But if you pick up real part, imaginary, you will consider their combination. But physically, we do not consider particle like linear combination of particle with charge plus and minus one. You see, so sometimes it's not good. Mathematically, you can do this, for sure. Okay. So this is crucial, extremely important relation, right? So field phi prime at point x now, including translations, let's consider the case when we including translation. Okay, let me just to have more space. So I consider so far for fields homogeneous transformation, right? And we got this fundamental, it's really fundamental relations. It's important. Lambda to the minus 1 x, but here x. And the same. Including translations. It's easy, you'll see. It's actually in a similar form, similar way. With respect to translations, no fields which change their form. They do not change form, right? Only X changes. In a similar way, we find that under translation x mu going x prime mu, which is x mu plus m mu, field phi x comes to the field phi prime x, which is equal phi x minus a. I meet this mu right in argument. So this is the same story. Inverse transformation. Direct transformation, x plus a should put x minus a. It's direct. Okay. Now, Lorentz invariant fields. How we can know that this field is Lorentz invariant, that really Lorentz symmetry satisfied for this particular case. Okay, I should know.
What do you mean by that?
Sorry?
All of our fields are representations of Lorentz groups, so they all automatically satisfy.
No, there are theories which are not Lorentz invariant. Let me define. You will see. Let me start. Not all theories are Lorentz invariant. It would be great. It's very strong symmetry. Yeah. And I will show you example non-Lorentz invariant. It will be easy. There are infinite and yeah.
You're talking about the Lagrangian.
I will talk about action and Lagrangian density. Please wait. Just I will define. Okay. Maybe actually I just all of this. Okay, let me put D, F. Okay. We start from Lagrangian density. So it depends. I will consider general case. And action definition. Theory is Lorentz invariant. if under the Lorentz transformation and I will write this. The Lagrangian density is transformed as a scalar field. It does not change the form, right? When M. So let me write more explicitly this. Lambda x under this transformation of field just going like that. Only argument changes, or more precisely, this is important, so I will write this guy, which is this, goes to this. Just we substitute this transformation. Which is, I just substitute those prime. And this, one should show this, is equal this. By I, A, okay, so Lagrangian, it's quite strong constraint. You substitute instead your phi initial d mu phi, their transformation written there, MAB, you change this argument, and then no M should be in Lagrangian. They should somehow cancel, and you have the same Lagrangian as before, only argument change. It's very strong constraint, and it does not satisfy always. I will show easily. Okay, this is important because it implies that action is invariant. Action does not change at all. This implies that action S, let me show this, which is nothing else, d for x lambda x remains unchanged. Let me show this. Okay, let's start. So maybe you should, right, please.
Strictly speaking, L can change up to a total boundary term that would integrate out.
Okay. Point is that this will be okay for Noether theorem. No. In principle, in this case, let me think. Let me finish this, right? And then we will come to your question. Okay, so I should show this, right? This stuff. Okay, so now action. It's actually not difficult. Okay, S, which is written here, changes to S prime, and this is D for X, but now I should put my Lagrangian density, but lambda minus 1x, because we proved, not proved, this was definition, right? That under transformation, L going to this point. Now, take y equal lambda to the minus 1x, change of variable, right? Then if I take this, what I have? I have this. Now, d for y and absolute value of Jacobian, change of variable, L, y. Now, what is Jacobian in this case? Y equal lambda 1x. It implies that Jacobian is determinant of Lorentz transformation. But we proved that this guy is plus or minus 1, just first class. Then absolute value is equal 1. So this guy equal d for y. And this is same action. Okay. Okay, now your question. Point is that I'm considering, strictly speaking, infinite space, because otherwise I would change boundary condition. Of course, boundary condition could change this, but still, theory actually is called Lorentz invariant when it means that it's Lorentz invariant in infinite space, because boundary condition always could break this. Point is that you could consider Lorentz invariant theory first in infinite space, but then study the theory breaking Lorentz invariant by boundary condition, which is quite interesting. Famous Casimir effect is connected with that. So boundary condition could change it. So I should say more rigorously that I'm considering infinite space. That's it. And then no surface steps, right? Because it's meaningless to consider on infinity. So this is, but this is practical definition, actually. You could eventually consider breakdown of Lorentz symmetry in Lorentz invariant. Many ways, like boundary condition changing, Or you could consider external fields. They change. You could put temperature. It changed. You could put density of particles, like electrons, like incandescence. All of them will break. But what is important that you have case in infinite space when this theory is Lorentz invariant. So this is the answer to your question, which is absolutely correct. Okay. Yes, please.
Relevant. So, how we define Lorentz invariant theories for theories which do not have Lagrangian?
Okay, I considering in this course only, of course, theories, Lagrangian theory, right? Point is that you could consider theories, but there are different possibilities, different examples. String theory has, for example, Lagrangian. For string, you could write. But you could consider so-called bootstrap theory where people do not have Lagrangian, they do not have Hamiltonian, but in that case, they have what is called S matrix. So you have S matrix which describes scattering of particles, and you put constraint, Lorentz invariant constraint for this S matrix. It was actually started by giant Werner Heisenberg. Heisenberg, during Second World War, this S matrix theory. So he proved that locality of the theory, which is nothing, essentially it's micro-causality, plus Lorentz invariance put very strong restriction on analytic structure of S matrix, and so on. Then you have unitarity and other things. But it's not easy without Lagrangian, without action to do this. But indifferent, it's like art. Fortunately, at this moment, it seems all important relativistic theories are Lagrangian theory, like quantum electrodynamics, and more important, even standard model. It's electroweak theory, we know Lagrangian, and quantum chromodynamics, we know Lagrangian. Even in the case of gravity, we actually cannot say that we know exactly Lagrangian because we know Einstein Lagrangian, Einstein Hilbert Lagrangian, or action. And but many people doubt, including me, that it's fundamental Lagrangian for quantum gravity, that it's mostly effective theory. But maybe it's wrong. I mean, I could be, and my friends so-called. Okay, this is answer to your question. Yeah, go ahead.
The thousand Lagrangian has some combination of the variables. So, you know, the Lagrangian system carries.
No, I consider, you see here, where it is. Here, I put general fields, not just scalar. So those fields transform in non-trivial way under Lorentz transformation, right? So not just scalars. But Lagrangian, what I said, is transformed under Lorentz transformation as scalar. Because look, I started from this and I finished after this chain, same function of fields, but only argument change, lambda minus x. If it transforms a scalar field, what I said was the following: if my Lagrangian density is transformed under Lorentz transformation as a scalar, and I will show that, for example, Klein-Gordon field and its Lagrangian density transform as a scalar. This I will show. But this is definition. If it transforms in this way, I did not prove this. I said, if it transforms, then the theory is Lorentz invariant. And action, what I showed, that in this case, action does not change. Equation of motion also does not change. Okay, this we will discuss. I will start next time class from considering the proof that Klein-Gordon, the simple theory we consider, is Lorentz invariant theory. And I show how easy to change Klein-Gordon to get non-Lorentz invariant Klein-Gordon theory.